Hello and welcome to Note Quiz number 11, where we talk about inverse functions and the exponential and log functions. This is the first part in a two-part set of notes talking about these functions, and the idea for this one is to kind of describe the relationship, how to graph them, and where they come from. So for starters here, we're going to talk about the definition of being a one-to-one function. And remember, with function notation, you have y is equal to f of x, and each x determines exactly one y. So for one-to-one, the idea is to look at the y numbers and to figure out what x numbers correspond to them. And if you have a y number where there's more than one x that corresponds to it, we say the function is not one-to-one. So one-to-one means that each y I pick will have exactly one x value to return back to if we're going reverse. And the easiest way to determine this is what's called the horizontal line test. You'll notice if I draw a horizontal line through this first graph here, it will intersect it in three places. And that means that there's actually three different x values that brought me to that one common y value. And that's not a good thing with one-to-one functions, because one-to-one functions, again, need to have that one y correspond to exactly one x. And in this case, for this line I drew, there's three. So this is not a one-to-one function. And again, it fails what's called the horizontal line test. For the second problem, you will notice that no matter where I draw a horizontal line, there's at most one x number that corresponds to that y value. So in this case, this function is one-to-one because, again, each y corresponds back to exactly one x. So that's the horizontal line test. And again, this passes the horizontal line test. So for graphs, it's pretty easy. Just apply the horizontal line test to see if it's one-to-one. For the next problem, you will notice that they're giving us a formula. And again, there would be nothing wrong with graphing this function and applying the horizontal line test. But to really emphasize the idea here, let's take two different x numbers. Let's calculate m of -2 and m of +2. When you calculate m of -2, you get -2 squared plus 1, which equals 5. And when you calculate m of 2, that is 2 squared plus 1, which also equals 5. So you have y equals 5 corresponding to two different x numbers, and that makes this function not one-to-one. And again, the shorthand notation for one-to-one is just one-to-one, like a score for a game. So again, this function is not one-to-one because that one y value of 5 corresponds to two different x numbers for inputs. And again, if we were to graph this function, it'd be a parabola, and it'd fail the horizontal line test. All right, so next up, we're going to talk about how to get a one-to-one function to give us an inverse. And an inverse function is really just a function that reverses the roles of the input and the output. Good examples of this pairing would be x cubed versus the cube root of x. If you plug 2 into x cubed, you get 8. And then if you took the cube root of 8, it'd take you back to 2. So those functions are inverses because they undo each other or reverse each other. So there's a 4-step process for finding inverse functions. And the easiest way to do it is to go through and first set the function equal to y. So we're going to first, and we'll call that step A, I guess. We'll just, call it A. So step A is to set the y equal to k of x. The second step of the process is to reverse. So with y equal to the cube root of x plus 2, we reverse the variables and have x is equal to the cube root of y plus 2. The next step is to solve for y. And we have to do a little bit of algebra to do this. And so in this case, we will cube both sides. And that cubing is going to give us an x cubed on the left And it's going to give us y plus 2 on the right because of the cancellation. And then we could subtract 2 from both sides. And that takes us down to y is equal to x cubed minus 2. The final last step is just to set your inverse notation, which is written with a -1 superscript. It is not a power or reciprocal, equal to what you got, which is x cubed minus 2. So for this problem here, our inverse function is x cubed minus 2. And again, the idea is that if you were to take this function, it would undo the mathematical operations of the original function k. All right, so now let's move on to the next example. And rather than labeling A, B, C, and D, let's just go through and work out the calculation. So again, first step, we're going to call it y. So y is equal to 3 divided by x plus 5. Next step, we swap. So that's going to tell us that x is equal to 3 over y plus 5. We now need to solve for y, and to do this, we're going to multiply both sides by the LCD, which is y plus 5. And we will cancel on the right and distribute on the left. So that is x times y plus 5 times x equals 3. We then subtract the 5x from both sides. And we get x times y equals negative 5x plus 3. And then finally, divide both sides by x. And you get the formula y is equal to negative 5x plus 3 over x. Or you can write it as a negative 5 plus 3 over x if you split apart the fraction. In any case, we kind of ran out of space there, so our inverse, g inverse of x, and we'll write it the original way, negative 5x plus 3 divided by x. So that is the inverse for the function g. And again, that function reverses the operations of the original function. All right, so let's move on to the next page. This page is going to start off with the relationship between the inverse graph and the original graph. And as we said earlier when we first started, the goal of the inverse is to reverse the operations of the function. So, and you saw in the calculation we just did that we are reversing the operations by reversing the x and the y. So first thing you want to do here is write down the ordered pairs for your original graph of a function. So your first ordered pairs are 2, 0, and then we got 1, negative 3, and then over here on the left side, we've got negative 2, negative 5. The inverse is going to reverse those ordered pairs. So if I start off with a 2, 0, I'm going to get 0, 2 as a point on the inverse function. And then if I take my 1, negative 3 and reverse those numbers, I get negative 3, 1. So that's going to be right over here at negative 3, 1. And then finally, if I reverse my ordered pair, negative 2, negative 5, that makes negative 5, negative 2, which is right there. And then if I connect my graph the way it's built, I'm going to have a line segment here and a line segment there. And if you look at this graph, you will notice that they are symmetric over a diagonal line. And that special diagonal line is nothing more than y equals x. So there's a diagonal line that divides this into two symmetric parts, and that line is y equals x. And you will always see that when you graph a function and its inverse, it is always symmetric over that diagonal line. And so graphing an inverse is easy as long as you reverse the ordered pairs and then connect your dots. All right, so now we're going to move on to what are called exponential functions, and they play a huge role in math and science and everywhere else around the world, including business and even biology, which is, I guess, science. The idea behind exponential functions is that this time around, you're going to have a base that is constant, and it's the exponent that is going to vary and take on different numbers. If you think about algebra, it is true that you can use any number you want as an exponent. We have positive numbers, which are just how many times you multiply. We've got the 0 power, which makes 1. And we've got negative exponents, which are reciprocals. And we have fraction exponents, which are radicals. So all these possibilities are covered. So we can use any number we want for our function, which means that the domain is going to be all real numbers. We can use anything that we want. So now let's go over here and make a table. If we make a table of x and y values, remember again, it is open season on whatever you want to pick for x. So let's pick -2, -1, 0, 1, and 2. Now these are going to be powers on the 2. So the first value is 2 to the 0. And remember, anything to the 0 power is 1. For the number 1, that's 2 to the first power, which is a 2. And then for 2, that's 2 squared, which is 4. Going backwards, if you put a -1 power on a 2, that gives you a half. And a -2 power on a 2 gives you a flip and a square, which is 1/4. So that's 5 ordered pairs for us to graph. Let's put them together into the picture. So when I take 0, again, I get a 1 for the y value. When I plug in a 1, I get a 2. When I plug in a 2, I get a 4. You'll notice that if I was to pick 3, I get an answer of 8, which is getting very big very quickly. Now going backwards, when I use a -1 power, I got a half for my value. When I used a -2, I got a fourth for my value. Those values are all getting smaller as I go to the left, but they will never reach 0 because there's always some number there. The next one is 1/8, then 1/16, and so on. So my graph is going to look something like this here. And it looks like a ramp that is starting off very slow and then growing forever. The other thing you'll notice here is there is a horizontal asymptote here because we have a line that's horizontal that we approach. And in this case, it's y equals 0. So because we have now a detailed graph, we can get our range from the picture. We know that the range is going to start at 0 and go up forever. It doesn't include 0 because we never reach the actual number 0. We get closer and closer, but never get there. And because we never reach 0, it is impossible for us to cross the x-axis and have an x-intercept, so there are no or none for x-intercepts. The y-intercept, it's actually in our table. It's the ordered pair 0, 1. There is no vertical asymptote, but you will notice there is a horizontal asymptote, which is y equals 0. So again, oops, let's get that out of there. No vertical. The answer is none. And again, y equals 0 is our horizontal. If you were to pick a base of 1/2, that's going to be a function that actually gets smaller as you travel from left to right. Again, on the right side, the 2 to the x gives you exponential growth. This is going to give you exponential decay. And we'll make a quick table here just to kind of show these points. We'll do them in blue just to be consistent. But again, I will just pick 5 values and do a quick computation. -2, -1, 0, 1, and 2. So the 0 power again on anything that's not 0 is 1. If you take a 1/2 and raise it to the first power, it's just itself. And then if you take a 1/2 and you square it, it's a 1/4. And then going backwards, if you take a 1/2 and take its reciprocal, you get a 2. And then if you take a 1/2 and you do a -2 power, that's a reciprocal and a squaring, that gives you a 4. You notice it's the same y values as the other table, they're just in reverse roles. So again, we've got a 0, 1, we've got a 1.5 and a quarter, and then going backwards, we've got -1, 2, and -2, 4. So we have a ramp again, but this ramp this time is going downwards towards the x-axis. And there's once again that horizontal asymptote of y equals 0. And we refer to this as exponential decay. Things that exponentially decay would be things such as radioactive materials, and the value of something when you buy it, and so on. To fill in our table down here, which really isn't necessary at this point, again, if I just pick three numbers for x, like -1, 0, and 1, the first one as a -1 power is just 1 over b, b to the 0 power is 1, and b to the first power is b. So in general, that's what it does to any number b. So again, that's how we look at our exponential functions. On the next page, we're going to start doing graphs that require transformations. So for the next page, you will notice that we're going to be looking at taking our basic graph, which was 2 to the x that we just had on the previous page, and we're going to be doing different things to it, including putting marks on our paper. There we go. So again, our basic function is 2 to the x. And then thinking about transformations, remember again that you always start with what would happen if you substituted a number in for x. So in the exponent, we're subtracting 1. Remember again, that is a horizontal shift 1 place to the right. So horizontal shift 1 to the right. And then when we add 1 to the whole function value, that's going to vertically shift us up 1 place because we're increasing all the y's by 1. So this is a vertical shift up 1 unit. So for our ordered pairs, we're going to move all of the x's 1 place to the right, which means we're going to be adding 1 to the ordered pair, first number. And then it actually ends up coincidentally that the y will also be added by 1 because we're moving up 1. All right, so from before we had our basic values. Remember we had -1, 0, 1, and 2. These again are going to be on 2 as a power. So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, and 2 to the -1 is a half. We are now going to take these 4 ordered pairs and transform them over. So let's first work on the x's. I'm going to increase all of those by 1. So -1 gets bumped up to a 0, 1 gets bumped up to a 1, 1 gets bumped up to a 2, and 2 gets bumped up to a 3. And then for the y values, we're going to increase them all by 1. Now, rather than dealing with improper fractions, it's actually better to write this as 1.5. because we're graphing. And then 1 plus 1 is 2, 2 plus 1 is 3, and 4 plus 1 is 5. So we now have 4 new ordered pairs to graph. We'll start off with 1, 2, because that's the easiest one to graph. And then 2, 3, and then finally 3, 5, which is right up here at the top. And then when I plug in 0, I get 1.5, which is 1.5 right between 1 and 2. Now remember before we talked about horizontal asymptotes, remember it was at 0. So if you're doing a transformation that is raising everything up 1 place, that horizontal asymptote is also being moved up 1 place. So instead of being at y equals 0, it's now at y equals 1. And now we can build the rest of our graph. We just kind of come down, and again, it's like a ramp going up that way. And now we can answer all these lovely questions about the graph. Again, the domain, all real numbers because it's exponential. So -infinity to infinity. The range this time starts at 1 and goes up forever, not including the 1. And again, our horizontal asymptote is y equals 1. So that is how we graph an exponential function using transformations. Let's now move on to the next page. And we're going to graph another one. This time around, however, you notice we have decay going on. So our basic function, it is now y equals 1/3 raised to the x power. And this time around, we actually have 2 transformations, and one of them is a little different. Having that negative in front of the function is going to reflect it over the x-axis. So this is a reflection across the x-axis. And then subtracting 2 is going to vertically shift down 2 places. So we have a vertical shift down 2 places. For our ordered pairs, the only thing that we're going to be doing is affecting the y numbers. We're going to be taking the opposite and then subtracting 2. So the x is going to actually stay the same in the transformation. And the y is going to be the opposite, and then we're going to lower it by 2. All right, so now let's look at our basic values. Again, let's take the same ones we had before for x, -1, 0, 1, and 2. This time around, our basic function is 1/3 to the x. So 1/3 raised to the 0 power is 1. 1/3 raised to the first power is 1/3. And then a 1/3 squared is a 1/9. And then a 1/3 to the -1 power is a flip. So you flip a 1/3, you get a 3/1. All right, so those x's we said are going to stay the same. And now the y's, we're going to take the opposite or multiply by -1 and then subtract 2. So the 3 is going to be -3 minus 2. That is -5. The 1 is going to be -1, take away 2. That is -3. The 1/3 is going to be -1/3 minus 2. Let's write that as -2 and a third. And then the other one is going to be -1/9 minus 2. That is -2 and a ninth. Again, these mixed numbers here make it really easy to graph. All right, so now let's talk about the horizontal asymptote. Since I'm subtracting 2 from the whole function, I'm shifting it down 2. So that vertical asymptote is moved down 2 places away from 0. And it is at y equals -2. I'm now going to plot my 4 ordered pairs. The easiest one to start with is 0, -3, which puts us right there. And then I've got a -1, -5, which is right there. And then I've got 1 for x and -2 and a third for y. So that's a little past the -2. And then the -2 and a ninth is a little even less past the -2. So I get my ramp that's going up this way and sharply turning and going down that way. That is the graph of that exponential function. All right, once again, we will find the different qualities of the function. The domain, not exciting. All real numbers, same as before. The range this time starts down at -infinity because it goes down forever, and it gets closer and closer to -2 without reaching it. So it is -infinity to -2, and we just saw in our picture, our horizontal asymptote is y equals -2. So that's another nice graph of an exponential function using transformations. And again, transformations make graphing so much easier than just plotting points and crossing your fingers. All right, so let's move on now to the next page. And the next page, we're going to begin doing what are called applications of exponential functions. And these are problems where you can no longer do these computations in your head. You have to have some sort of scientific calculator. So I worked out these values in advance so I wouldn't have to be trying to be typing and clunking away at a calculator while answering the questions. So when I get these numbers, it's not that I'm some super psychic. It's because I actually have them written down in advance. And I'll talk about how to use a calculator to get these numbers in a few minutes. All right, so for our first problem here, we have a radioactive decay, and it's going to be a situation where we've got a substance called polonium, and it decays by half every 138.4 years. That's its half-life. And we can use this exponential function. And again, it's an exponential function because the variable is in the exponent. And it's going to give us the amount that remains after t years has gone by. So for us, we want to find out how much is left after 500 years. We just calculate a of 500. And it's a good idea to write this out first physically on your paper you're working with. So that's a 0.8 times a 1/2 raised to the 500 divided by 138.4. And again, that is your exponent. So when you're doing computations on a scientific calculator, you want to make it as easy as possible. That is 0.8 times, and then you have a base of 1 divided by 2 in parentheses, and then you probably have a power button. It's either a caret, which is the shift 6 on the keyboard, or it's the X to the Y button. I'm going to assume it's a caret because it's the calculator for our class. And then for this power, use parentheses. It is 500 divided by 138.4. And when you hit the equals button or the enter key, you should get roughly 0.065 if I round to 3 decimal places. And because we're doing an application problem, you want to make sure you put units on your answer so people know how much you actually have. So that is milligrams for this problem here. And so to translate our answer, it is going to be after 500 years, that was our t value we plugged in, we have 0.065 milligrams remaining. And again, that 0.065 came from a calculator. We cannot get those numbers in our head. All right, so that's our first example of an exponential application. Now let's take a look at problem 10. And this is a problem that models inflation. The idea is that in the year 2010, if you had $100 of buying power, as time passes, that power goes down. That money is worth less. $100 back then is probably worth 90 now. Who knows? It kind of depends on inflationary rates, and they always change all the time. But my exponential functions are good for modeling such things. So in particular, they want us to use the function to predict or calculate A of 25, where 25 is the number of years since 2010. So when you do calculate A of 25, again, that is done on your scientific calculator. That is 100 times e raised to the 0.0 times the number 25. And you will notice again, I'm using parentheses around my exponent because I want to multiply those numbers and then use them as a power. So once you type this into your calculator, and again, you may have to look for the E button on there. You may have to hit the second key to trigger it. But when you do this calculation, you are going to get approximately 221.44, which says that you have to have $221.44 in the year 2035 to have $100 of buying power back in 2010. Kind of depressing, but that is how it works out. So again, 221.44. So we need to have $221.44 in 2035 to have the buying power of $100 in 2010. All right, and then there's another part of this question. They want us to verify that by the year 2032, you will need more than $200 to have the buying power of 100 back in 2010. So once again, we just calculate. Remember again that the time starts at 2010. So we actually need to calculate A of 22 because that is going to be 22 years past 2010. So we calculate A of 22. And when we do that, again, symbolically, it is 100 times e to the 0.0318 times 22. But on a calculator, that is 100 times e raised to the power 0.0318 times 22. And that works out to be an approximate decimal. That is 201.29. And that should tell us right there that we definitely need to wait that many years to get that value because we need to be over $200 according to the question. So again, that is a 201.29. And so again, 201, we'll write it so many times because I just erased it. All right, so again, that is our answer to that question there. And again, it's a model. It's not exact. That could be off a little bit depending on how things change over time. All right, so let's move on now to some more applications. The next one is a cooling problem. This problem here models Newton's law of cooling, which says that something cools off at a rate proportional to the difference between the temperature of the object and the temperature in the room. In other words, if there's a bigger temperature contrast between the object and the room, it cools off much faster at first, and then as the temperatures get closer together, it starts slowing down. So in this problem here, we have a whole bunch of what are called constants. We have a TA, that is the temperature of the air in the room. Again, T sub A is that value. T0 or T sub 0 is going to be the temperature of the object that you're studying. And then K is some predetermined constant that tells you how fast it actually cools. So for this problem, they tell us that 72 is the temperature of the room, and we're taking a cake out of the oven at 400 degrees. So our exponential function for this problem is going to be T, the temperature of the thing, whatever it is, the time it's a cake, at time T, two different uses there for the letter. One is capital, one is lowercase. That is 72 plus 400 minus 72 times e to the negative 0.046t. So that is our exponential function. Of course, I can simplify. 400 minus 72 is 328. So when I write my function down, it's going to be 72 plus 328 times e to the negative 0.046t. And we haven't really talked a lot about e in this class, but what it is going to be a natural number that we see in science. And this number is going to be something that makes all of our mathematical formulas in science easier to work with. So, and again, you'll probably see more of it coming up in other classes down the road, especially if you take pre-calculus. All right, so next up, we're going to go through and answer some questions using this function we just built. They want us to find the temperature of the cake 10 minutes after we take it out of the oven. So that's the temperature at time 10. That is 72 plus 328 times e to the negative 0.046 times 10. On your calculator, that is just literally 72 plus 328 times e raised to the negative 0.046 times 10 in parentheses. And when you do that, you should get approximately 279 degrees. That is still a very hot cake. We assume, of course, this is Fahrenheit. Can't imagine it as Celsius. All right, and then the question is, if you're going to be putting frosting on this cake, you better make sure that the cake is cool enough to do so. We want it to be under 100 degrees. So the question is, if we wait 55 minutes, will the temperature fall below 100 and be cool enough to put frosting on the cake? And obviously, if you put frosting on a very hot cake, it melts and goes everywhere. So we want to calculate the temperature of the cake after 55 minutes. And it's going to be, again, 72 plus 328 times e to the negative 0.046 times 55. In your calculator, that's just 72 plus 328 times e raised to negative 0.046 times 55. And that works out to be roughly 98 degrees. So yes, that is under 100. So that is the answer to our question. The cake is going to be cool enough to put frosting on it because it's down to 98. All right, so those are some exponential applications. You'll see more of those coming up in note quiz number 12, where we'll actually go and do things in the reverse order, where we want to find out how long it takes for the cake to reach a temperature. So stay tuned for that. In the meantime, we're now going to switch gears and talk about what are called logarithm functions. And logarithm functions are nothing more than just the inverse of the exponential function. So there's an important formula here that I wish I would have had typeset into the notes for reference, but we'll write it down so we have it available for us. And it's the equivalence between exponential and logarithmic. So if you know that y is equal to b to the x, that is the same thing as log base b of the number y equaling x. In other words, it's going to be the inverse function because we're reversing the role of the x and the y. In other words, you give me a number, I figure out the exponent. That's really the job of the inverse function called a logarithm. So for this first problem here, we're going to convert the logarithm into exponential form. And that's going to be 2 raised to the 5th power is equal to 32. And what's really nice about these problems here is you can actually check to see if that makes sense. And it is true that if you take 2 and multiply it by itself 5 times, you do get 32. The next problem is a little bit confusing because it feels a bit out of place, but this ln is called a natural logarithm. I'll write that in green. And that is where the base of the logarithm is written in shorthand as an e. So this is really the same thing as log base e of 1 is equal to 0. So when I write that over as an exponential, the base is the number e, the power is 0, and the answer you get would be 1, because anything to the 0 power is 1. So again, ln is our really brief way to write the natural log, or the log with the base of e. Kind of just an abbreviation. So for the next problem, we're going to go in reverse. We're going to actually take an exponential statement and write it as a logarithm. When you do this, you want to make sure that you capture the base and put that as a subscript on the log. So you're going to have the log, the 3 letters for that function, then a subscript with the base of 6, and then you have the number you're taking the log of, and then you have that equal to the exponent. So that's read log base 6 of 36 equals 2. For the next one, similar story. Log base 1/2 of the number 16 is equal to negative 4. And again, that's telling you that if you take the number 1/2 and raise it to the negative 4 power, you get an answer of 16. Again, that is the job of exponents and logarithms. They're inverses, they undo each other. So for the next page, we're going to go in and actually calculate some logarithms using this definition. So for the first problem, you're going to be asking yourself, what power would I put on a 9 to get 81? And of course, that power is 2. So the answer to that logarithm is the exponent 2. For the next problem, they're asking you 10. It's a common log. There's a little invisible 10 here, kind of like how there's an invisible 2 on a square root. 10 raised to what power equals 1 over 100,000? And when you think about it, you have to think about the fact that negative exponents are reciprocals. So it's going to be a negative number. And then 10 to the 5th makes 100,000. So that power is negative 5. And you can actually verify that on your calculator by just typing in that number and hitting the log button, or typing it in on different calculators as a log first. For the next one, this is a question about the number e. It's asking you e to what power is equal to 1 over e to the 9th. And again, it's got to be a negative because it's a reciprocal, and it's a 9th power to make, well, a 9th power, if you will. So the next one, that is taking the base of 1/2, raising it to a mystery power to get an answer of 1 over 512. So when you do this problem here, you might want to get your calculator out and kind of do some multiplication with trial and error. If you keep multiplying this out by taking 2 times 2 times 2, ends up being the 9th power. So 1/2 raised to the 9th gives you 1 over 512. All right, so now let's move on to our logarithmic functions in general. With logarithmic functions, remember again, they are inverses of exponentials, so everything is reversed. And what you're looking at is really a question about exponents. So if you make a table to graph your function, what you want to do is take powers of 2. So in other words, we will take the number 1/2, the number 1, the number 2, and the number 4. And we don't need to go any bigger than this because we'll end up not being on the picture. So if you ask yourself this question, 2 raised to what power makes a 1? That power is 0. If you ask yourself this question, 2 raised to what power makes 2? It's 2 to the first power. That makes 2. Then you ask yourself, what power would you put on a 2 to get a 4? It is 2 squared. And then going backwards, what power would you put on a 2 to get a half? That's a reciprocal. That's a -1. So we now have 4 ordered pairs to graph. Let's put them on our picture. Again, we've got 1, 0, we've got 2, 1, and we got 4, 2. And we also have 1/2, -1. So our graph is looking like something like this here. And we have what's called a vertical asymptote. We have a vertical line till we get closer. If you think about it, the next number going up my table would be a quarter. That'd make a -2. If you go to an eighth, that'd make a -3. So those smaller and smaller positive fractions give you much more negative answers. So in this case, you'll notice that we have logarithmic growth. It is growing and going upwards. And if you think about it, that horizontal asymptote from the exponential function became the vertical asymptote of the log function. You will also notice that my domain and range are going to be different. Before we do that, let's draw our other graph. Let's take our same x and y. I'm going to take the same numbers. So I'm going to take a half, a 1, a 2, and a 4. Remember, this time around, we're looking at powers on a half. So anything to the 0 power is 1. So the log of 1 is always going to be 0. 1/2 raised to the first power makes a half. If I want to turn a half into a 2, I have to take the reciprocal, -1. And then if I want to turn it into a 4, that's a flip and a square. You notice it's the same values as before, well, more or less, but they're, again, kind of reversed in their order. Plugging in and plotting, here's my 1, 0. Here's my 2, -1. There's my 4, -2. And then my 1/2, 1. And again, if I was to look at a quarter, it would be 2. So my graph looks like this. It's kind of a ramp going downwards. And once again, I've got a vertical asymptote at the point x equals 0. All right, so now we're ready to answer the domain and range. The domain, you'll notice, the graph starts at x equals 0 and goes to the right. So that's going to be from 0 to infinity. You'll notice the range goes down forever and it goes up forever with no breaks or gaps. So my range is all real numbers. My x-intercept, this time around, it crosses through 1, 0. My y-intercept, I don't have any because I get closer and closer to the y-axis, but I don't touch it. So I've got none. I do have a vertical asymptote. It's at x equals 0, and I have no horizontal asymptote. You will notice here that these are the same answers from exponential functions, but they are reversed. And again, don't be surprised. That is the job of the logarithm. It's the inverse, therefore it must reverse. Now when you do our table down here for our values, let's pick b. Let's pick 1 and 1 over b. The answers are going to be b to the first makes b, b to the 0 makes 1, and b raised to the -1 power makes that reciprocal 1 over b. All right, so that's how our logs are going to look. Now for our last problem, let's go through and graph one using transformations. So graphing using transformations, we're going to be looking at moving the graph around again. But I guess before we do that, I forgot there's a domain question. Let's talk about that as well. You just saw on the previous page that the logarithm starts at 0 and goes to the right. And what that means is that the stuff or the argument in this logarithm must be positive because you are to the right of 0. So 4x plus 8, the inside of the log must be positive. So that says that 4x is greater than -8. And dividing by 4, that says x is greater than -2. So your domain is going to be from -2 to infinity for that particular log function. You'll notice here it's got nothing to do with the base of 3. The base has no role in determining the domain. All right, so next up, now let's look at graphing a log function using transformations. First thing you want to do is identify your basic function. It is y equals log base 2 of x. And then you'll notice we've got two transformations here. Adding the 4 inside of the function is going to shift it 4 places to the left. So that's a horizontal shift left by 4. And then subtracting 1 from the whole function is going to be a vertical shift. That is down 1. All right, and that's it for transformations, just 2. So when you shift to the left, that's going to decrease your x-coordinate by 4. So we subtract 4 from that. And then when we shift down 1 unit, that's supposed to be an n there, that's going to be y minus 1. So let's erase that. That is a very strange looking n. There we go. Let's make it nicer. And again, down 1. All right, so for our basic function, we just saw these numbers on the previous page. If you take a half, a 1, a 2, and a 4, again, I'm taking powers of 2. It is 2 to the -1 that makes a half, 2 to the 0 that makes 1, 2 to the first that makes 2, and 2 squared that makes 4. All right, now I'm going to transform all of these. And I'm going to start with the easier one first. If I take a 1 minus 4, that makes a -3. If I take a 2 minus a 4, that's a -2. And then a 4 minus 4 is 0. And then back there, if I take a half and take away 4, that is -3 and a half. Now for my y numbers, I'm just going to subtract 1 from all of them. So -1 take away 1 is -2, 0 take away 1, -1, 1 take away 1 is 0, and 2 take away 1 is 1. All right, next up, I'm going to plot those new ordered pairs. So I've got 0, 1, which is right there. I've got -2, 0, which is right there. I've got -3, -1, which is right there. Then I got this -3.5, -2, which is right around there. So I'm going to draw my graph, and before I do it, it's probably a good idea to think about that vertical asymptote. Remember, it used to be over here at 0, but we're moving it 4 places to the left. So my new vertical asymptote is going to go up and down through -4. Again, I just picked it up and moved it 4 places to the left. All right, and then from there, I can draw my graph. It's going to be this nice increasing ramp that goes up and over that way. It keeps on growing to the right and going down to -infinity on the left. getting closer to that vertical asymptote. And from there, I can now answer my questions. My domain, it starts at -4 and goes forever to the right and excludes -4. My range, it's always going to be all real numbers for your basic logarithms. And then my asymptote is going to be x equals -4. It's that vertical line passing through -4. And that takes us to the end of our note quiz. So again, when you're graphing exponentials and logs, try to use transformations because they make it a lot easier. And more importantly, try to remember the inverse relationship between exponential functions and log functions. It will save a lot of time for you and help you make common mistakes. So again, remember the logarithm and the exponential function are inverses when they have the same base. And hopefully that helps you with your homework and doing well on the upcoming tests.